Hello, my dear students. Let us continue with the topic, the various forces acting on the dam. The next force is silt pressure. The river brings silt and debris along with it. The silt load gets deposited to an appreciable extent when the dam is constructed. The dam is therefore subjected to silt pressure in addition to the water pressure. If gamma S dash is the submerged unit weight of silt and phi is the angle of internal friction and Hs is the height to which the silt is deposited, then the silt pressure is given by Ps, that is silt pressure, is equal to half into gamma S dash into Hs square into 1 minus sin phi divided by 1 plus sin phi. This is nothing but K half into K into gamma into H. In the earth pressure you have learned the same thing here. Instead of K it is written 1 minus sin phi divided by 1 plus sin phi. Okay, so half into base into height into Ka. So half into gamma S dash into Hs square into 1 minus sin phi by 1 plus sin phi. That is the silt pressure. If the upstream face is inclined, the vertical weight of the silt supported on the slope also act as vertical force. According to Indian Standard IS 6512-1984, silt pressure and water pressure exists together in submerged silt. There are some criteria is recommended for calculating the forces due to silt, that is like horizontal silt and water pressure, that is assumed to be equivalent to that of a fluid weighing 1360 kg per meter cube or 13.34 kilonewton per meter cube, and vertical silt and water pressure is determined as if silt and water together have a density of 1925 kg per meter cube or 18.88 kilonewton per meter cube. Since the horizontal and vertical components due to water have already been taken with the W is equal to 1000 kg per meter cube or 9.81 kilonewton per meter cube, the additional force due to silt alone are computed by taking gamma S dash, that is equal to 1360 minus 1000, that is equal to 360 kg per meter cube or 3.53 kilonewton per meter cube for horizontal pressure, and gamma S dash is equal to 1925 minus 1000, that is equal to 925 kg per meter cube or 9.07 kilonewton per meter cube for vertical pressure. Okay, so this is about silt pressure which is acting here. Okay, PS. Next, the force is wave pressure. Waves are generated on the reservoir surface because of the wind blowing over it. Wave pressure depends on the wave height. Wave height may be calculated from the following formula, that is HW is equal to 0.0322 square root of vertical force plus 0.763 minus 0.271 into F to the power 1 by 4 for F is less than 32 kilometer, and HW is equal to 0.0322 square root of vertical force for F is greater than 32 kilometer, where HW is height of waves in meter between trough and crest, and V is wind velocity in kilometer per hour, and F is fetch or straight length of water expanse in kilometer. The pressure intensity due to waves is given by PW is equal to 2.4 W into HW. The figure shows the configuration of the wave and the approximated wave pressure distribution diagram. Okay, this is the abstracted crest, approximated pressure line, unobstructed crest, still water level, wave pressure, intensity. The pressure intensity due to waves is given by 2.4 W into HW, where PW is the maximum unit pressure which occurs at 1 by 8 times of HW above the still water surface. The pressure distribution is curvilinear. However, for design purpose, the pressure distribution may be assumed to be represented by a triangle of height equal to 5 by 3 of HW. This height, 5 by 3 of HW. Hence, the total pressure PW is given by PW is equal to 2.4 WHW into half into 5/3 of HW. So we will get, when we simplify, that is equal to 2 into WHW square, which is acting at a height of 3 divided by 8 times of HW above the reservoir surface. Okay. The next one is wind pressure. It is a minor force and need hardly be taken into account for the design of dams. Wind pressure is required to be considered only on that portion of the superstructure which is exposed to the action of wind. Normally, wind pressure is taken as 1 to 1.5 kN per meter square for the area exposed to the wind pressure. You can see here, which is acting here in this direction. Next one is ice pressure. The ice pressure is more important for dams constructed in cold countries or at higher elevations. The ice formed on the water surface of the reservoir is subjected to expansion and contraction due to temperature variations. The coefficient of thermal expansion of ice being 5 times more than that of concrete, the dam face has to resist the force due to expansion of ice. This force acts linearly along the length of the dam at the reservoir level. IS 6512-1984 recommends that till specific reliable procedure become available for the assessment of ice pressure, it may be provided for at the rate of 250 kN per meter cube applied to the face of the dam over the anticipated area of contact of ice with the face of the dam. The magnitude of this force varies from 250 to 1500 kN per meter square depending upon the temperature variations. The next one is earthquake pressure. Dams are subjected to vibration during the earthquakes. Vibrations affects both the body of the dam as well as the water in the reservoir behind the dam. The most danger effect occurs when the vibration is perpendicular to the face of the dam. Due to vertical earthquake acceleration, the dam as well as reservoir water are accelerated vertically upwards and downwards. This is resisted by the dam and water owing to their inertia. Hence, the effect of vertical earthquake acceleration is to change the unit weight of water, W, and the dam material, Wm. An acceleration upwards increases the weights and an acceleration downwards decreases the weights. The waves impact accelerations to the foundation under the dam and causes its movement. In order to avoid the rupture, the dam must also move along with it. This acceleration introduces an inertia force in the body of the dam and sets up stresses initially in lower layers and gradually in the whole body of the dam. Earthquake wave may travel in any direction. However, it is customary to resolve the general direction of the acceleration into horizontal and vertical directions. The intensity of an earthquake at a place is a measure of the strength of shaking during the earthquake and is indicated by a number. There are world maps which are divided into different zones according to the severity of earthquake. Among to IS 1893-1984, India was divided in 5 zones: Zone 1, Zone 2, Zone 3, Zone 4 and Zone 5. However, according to its revised version, IS 1893-2002, the seismic zone map is revised with only 4 zones instead of 5. Then spectra of earthquake. The spectrum of an earthquake is the representation of the maximum dynamic response of idealized structure during an earthquake. The idealized structure is a single degree of freedom system having a certain period of vibration and damping. The maximum response is plotted against the natural period of vibration and can be expressed in terms of the maximum absolute acceleration, maximum relative velocity, and maximum relative displacement. For the purpose of design, acceleration spectra are very useful as they give the seismic force on the structure directly by multiplying it with the generalized or model mass of the structure, that is, force equal to mass into earthquake acceleration. The earthquake acceleration is usually designated as fraction of the acceleration due to gravity and is expressed as alpha into g, where alpha is known as seismic coefficient. And there are many design criteria for this seismic coefficient for the different zones, like seismic coefficient method, response spectrum method, etc. Okay. So, and also there is effect of horizontal earthquake acceleration. Mainly, horizontal acceleration due to earthquake causes two effects. The first one is inertia force in the body of the dam, and second one is the hydrodynamic pressure of water. The horizontal inertia force is the product of mass and acceleration, and this force acts in the direction opposite to that of the ground motion. The horizontal inertia force acts from the upstream to downstream as well as from downstream to upstream. Whereas hydrodynamic pressure of water, the horizontal acceleration of the dam and the foundation towards the reservoir causes a momentary increase in water pressure since the water resists the moment owing to its inertia. The additional water pressure over and above the static water pressure is known as hydrodynamic pressure. So this is about earthquake pressure. I hope all of you understood. Thank you.